Hello, welcome to today's lesson on the property of waves. The first thing we need to look at is light. So the electromagnetic spectrum is a range of wavelengths that light can exist in. An electromagnetic wave is simply a light wave. However, we reserve the term light for part of the spectrum that we can see. This is called the visible spectrum. Other parts of the spectrum have different names. It's important to note that each type of wave is a light wave, but just has a different wavelength and behaviors and purposes. So the visible light spectrum is what we can see, and is usually this rainbow here. Shorter or longer waves include radio and microwaves, and shorter waves include gamma and X-rays. Some definitions. A luminous body is an object that emits light. An example of that is the sun. A non-luminous body does not emit light but reflects or absorbs it. These are often referred to as illuminated bodies. An example of this would be the moon, as the moon reflects the light from the sun for us to see. An incandescent body is an object that emits light when it is heated. The type or color of light it emits depends on its temperature. An example of this would be a light bulb with a filament. Those really round bulbs that aren't used as much today, but the filament in the light bulb, that's the part right there that would light up. Light naturally travels in a straight line. This is called rectilinear propagation. Light only does not travel in a straight line when it passes through a strong gravitational field. A transparent object will transmit light while it absorbs or reflects them as well. So an example of this would be glass. Translucent objects will scatter and transmit light, but does not allow the object to be clearly seen through them. So that would be something like paper with oil on it. And the last kind of object is an opaque object, which is neither translucent nor transparent. These objects either absorb or reflect wavelengths of light. Most objects are opaque. We can represent the path light follows on paper by drawing ray diagrams. Rays do not actually exist in nature, but they are a geometric construct that help describe the nature of light. A beam is thought to be a collection of rays. Shadows form when an opaque object is placed in the path of light. We call a total shadow an umbra, and a partial shadow a penumbra. And a partial shadow usually shows up around the full shadow, and it's kind of fuzzy. A wave is a transfer of energy in the form of a disturbance propagating through a medium. There are two general types of waves, transverse and longitudinal. Transverse waves occur when a vibration of a medium is perpendicular to the direction of the energy transfer, so up and down, if the energy is moving forward. The maximum position of a transverse wave is called the crest, the very top of the wave. The minimum position of a transverse wave is called a trough, the very bottom of the wave. Amplitude is the maximum distance or the equilibrium or of the equilibrium or the rest place. So between the top of the wave and the rest place where the wave isn't moving at all. The wavelength, or lambda, is the distance between the successive crests or troughs. So one wavelength will go to the top of one trough, or one crest to the very top of the next, or the bottom of one trough to the very bottom of the next. You can also say the one wavelength could go from where it meets its resting place to the next resting place. That would also be one wavelength. Longitudinal waves occur when the medium vibrates parallel to the direction of energy transfer. These waves are caused by the cycle of compressing and recoiling particles in the medium. You can kind of think of this as if you have a slinky that you've stretched out and you pull a little bit of the slinky back to you and then let it go, and it's going to kind of bounce back and forth down the slinky. The regions with little space between particles are called compression. The region with particles where the particles are spaced out are called refraction. So we have compression, we have refraction. While waves move through a medium, there is little permanent displacement of the particles in the medium. That is, the particles tend to move back to their original place of rest. A pulse is a wave with a short disturbance. One complete oscillation or passing of a wave is called a cycle. Therefore, this would be from crest to crest or trough to trough. Okay, so or the same place in the refraction to the next same place in the refraction, or the same place in the compression to the other same place in the compression. The frequency formula. Here's where the math comes in. Waves that vibrate in repeated cycles illustrate periodic motion or harmonic motion. With the frequency f describes the number of cycles passing a point in a given time unit. The unit for frequency is hertz, which is actually cycles per second. So your formula is f equals the number of cycles divided by the change in time, where f is your frequency and delta t is your time interval. So here's an example. 12 waves in a pool pass a buoy in 10 seconds. What is the frequency of the waves? So we're going to set this one up the same way we always have set up these kind of questions. We'll write down our formula. F equals number of cycles over change in time. We're going to write down our knowns and unknowns. F equals number of cycles equals change in time equals. So the question tells us that there are 12, that's an ugly color. There are 12 waves, so that's the number of cycles, and they happen in 10 seconds. So then we can sub and solve. F equals 12 over 10. 12 divided by 10 is 1.2. And remember, the unit for frequency is hertz. The period formula. The time required for a full wave to pass a point is called the period, or t. So t equals the change in time divided by the number of cycles. So where t is your period and your small t is your time in seconds. What is the period of the wave of 18 waves that pass a point in 33.6 seconds? Okay, same thing. Our period equals our change in time over our number of cycles. Knowns and unknowns, we're looking for the period. Our change in time is 3.6 seconds, and our number of cycles is 18. We sub in t equals 3.6 divided by 18. And when I plug that into a calculator, I end up with t equals 0.2. Frequency and period are reciprocals of each other. So remember, reciprocal means that you have flipped the fraction. So your numerator becomes your denominator, and your denominator becomes your numerator. So f equals 1 over t, and t equals 1 over f. So this should be a power of 2. So if the frequency of the wave is 2.77 times 10 to the power of 2 hertz, what is the period? So we're looking for period. We know that the frequency is 2.77 times 10 to the power of 2 hertz. So we sub in t equals 1 over 2.77 times 10 to the power of 2. And when I plug that into my calculator, I end up getting 0.00361. The universal wave equation formula. All forms of light have the same speed. However, or whether it be a radio wave, infrared, visible, or X-rays. However, each set of waves has a range of wavelengths. Furthermore, they also have a range of frequencies. The universal wave equation is a relationship between the frequency, speed, and the wavelength. The formula is V equals F lambda, where V equals the velocity in meters per second, lambda equals the hertz in meters, and lambda equals the wavelength in meters, and F equals the frequency in hertz. An electromagnetic wave has a frequency of 1.00 times 10 to the power of 13 hertz. What is the wavelength of this light? What type of light is the wave probably classified as? Alright, so our formula here is V equals lambda F. B is the velocity of the wave, and the velocity of all of these light waves that we will look at is always going to be 3.00 times 10 to the power of 8 meters per second. Now that is the speed of light. Our lambda is given to us in the equation as 1.00 times 10 to the power of 13 hertz, and it's asking us to look, the frequency, and then it's asking us to look for the wavelength. So we have to we can sub and solve, but we're not solving for V. So I would rather do the algebra right now and figure out the equation that we're actually going to use. So V equals lambda F. We have to divide by F on both sides to get rid of it. So then we end up with the equation lambda equals V divided by F. Now we can solve nice and easily. So lambda equals 3.00 times 10 to the 8 meters per second divided by 1.00 times 10 to the 13 hertz. Okay, and when I do the math on my calculator, I end up with my lambda equaling 3.00 times 10 to the negative 5 meters. So if I pull up the electromagnetic spectrum, 3 times 10 to the negative 5 fits in right about here for my wavelength, which means it would be infrared light. I can't spell. Okay, another example. We need to remember that we can calculate the speed of an object with the formula that you would have learned in grade 10, velocity equals distance times time. A wave having wavelength 3.6 meters travels 2.0 meters in 1.25 seconds. What is the period of the wave? Alright, so we kind of have to go through a little bit of all that we've learned today. So first we have to figure out what the velocity of our wave was. So V equals dt. V we don't know. D is 3.6 meters, the distance. Nope. That 3.6 is the wavelength. So we need to know the distance it travels. So it travels 2 meters in 0.125 seconds. So 2 meters, the t equals 0.125 seconds. So we can sub in. V equals 2 times 0.125 equals 0.250 meters per second when I sub it into my calculator. Okay, so to figure out period, we need to know the frequency. So remember, we can figure out frequency with the formula V equals lambda F. So we'll figure out we're looking for frequency. So F is what we're looking for. V is what we just found. The wavelength is what's given up here, is a 3.6 meters. Okay, I just want to solve for our frequency. So to do that, remember we're going to V equals lambda F, divide by lambda on both sides. So the lambdas cancel out, and our F equals V over lambda. So F equals 0.25 over 3.60. Okay, and when I sub that into my calculator, I put that into my calculator to solve, I get 0.069. Remember, frequency is in hertz. Oh, for some reason that decided it needed to stay big. So remember, our period is 1 over frequency. So t equals 1 over 0.069. So t will equal 14.5. All right, that is the end of today's lesson. If you have any questions, please let me know tomorrow in class. Have a good night.